Okay, let's take a look at these. This is the other of the two applied assignments is up. There's the optimization one, which is, okay, that's probably a grizzly bear.
What?
This one is just a,
Wait, what?
this one's just a black bear. It's not that bad. Yeah.
I don't know.
Wait, what about
I don't
Kodiak bears?
understand
You
this.
sure it's not Kodiak bear?
What's
Polar
that?
bear. Kodiak
No,
bear.
I'd say grizzly. I'd say grizzly. If I had to grade it out, I'd say
Giant,
grizzly.
giant panda bear. You know?
No. No, they're just cuddly, aren't they?
Yeah, they're just.
No, they're really stupid.
Okay, here we go. So these are the kinds of questions you see on there. I just grabbed a couple, like one of each different kind. Let's take a look at these. They want you to find the linearization L of x at x equals a. All that means, this is a little different language. This is the language of the Math Excel stuff. That's okay. It's not an uncommon word. It doesn't show up in our text. All that means is the linear model. Find the linearization means what's the, if we take x equals a to be the point of tangency, what's the tangent line is all it is, right? The tangent line to the curve is the linearization. That's what we're going to use for our linear model, okay, if we want to do an approximation. So this is no big. We've done these problems already. We did a bunch of these earlier in the year. How do we find the tangent line to a curve at a given value of x? Find the derivative. Good. Okay, so let's find, we want to find f prime of x, which is okay. Good. And then what do I do with the derivative?
You gotta find the test points.
Well, no, you're no, I don't need any of that stuff. If I just want to find the equation of a tangent line, what are the two ingredients for the equation of a line? Slope and a point. Right. Well, we know the point. The point is that x equals 2 and y is whatever it is, right? We can plug in 2 in for x and find y. So there's our point. We need the slope of the tangent line. How do we get that? But how are we finding it? What's the slope of the tangent line at x equals a? Into where? Derivative. Sure. That's what the derivative does. It tells us the slope of the function, right? So the slope of the tangent line is just equal to f prime of a, f prime of 2, right? So 9 times 2 squared plus 2, so it's big. What is that? 9 times 4, 36. So 38 is the slope. Okay. Wow. And then if I want to find y, the y coordinate, I know, is the value of the function evaluated at 2, right? 38. So that's going to be 3 times 2 cubed plus 2 times 2 minus 1, which is what? 24 plus 4 is 28 minus 1, 27. Did I do that right? 24. Yeah, I think so. Okay. So then we've got the point, 2, 27, and the slope, m equals 38. All we have to do is make a line out of that, right? So we could just say, we just need b, right? We have m, so let's just throw everything in the equation and solve for b. So 2 goes in for x, 38 goes in for m, 27 goes in for y, solve for b, and b equals what? 27 over 76? Everybody buy that? Okay. So then y just equals m, which we said was 38.
Yeah,
What's that?
Actually, yeah.
Oh, never mind. You're right. Whoops.
Yeah.
See if you're paying attention. Yeah. Okay, so 27 minus 76 is what?
Negative 40.
49.
Guys.
There we go. Okay. 27, yeah, there we go. So negative 49. So then we just get the equation y equals m, which we found to be 38x plus b. So that's our linearization. That's the line. They call that L of x. Yep,
That's the equation.
Yeah. that's it. That's the equation of the tangent line. No big deal.
And that's called finding the linearization.
Yep.
Yep. So the linearization is just the tangent.
Linearization is just the linear model. Yeah, it's just the tangent to the curve at that point. Right. Okay, moving on. They're going to ask you to do one of these. One of these party tricks.
No. Are you serious?
Yeah,
We'll just find them.
a couple of these. This is 3.9.
So it should be nice, 100 money.
Okay, so to get these now, to get our thinking straight on these, if you do these right, they're no big deal, right? We know that delta or dx, excuse me, dy just equals f prime of x dx, right? That's our differential approximation. Okay, that's the approximate change in the function, right? And so then what we want to do here is we want to say the f of x plus delta x is approximately equal to f of x plus dy, right?
That's right.
Yeah.
These aren't going to be on the test, right?
Yeah.
Yeah.
Now I'm going to give you one of these on the test.
Right.
Okay. So then now think what that means. All that's saying is this. Think of this in terms of the picture. Pictures are invaluable in calculus. If you remember the pictures, you got it made. If you can draw the pictures, in fact, I can remember lots of times, like in college, when I'd sit down to do a big calculus final or something, I would sit there and I'd draw the picture first.
Did you take an art class?
No.
Question.
So if that's x, and that's x plus delta x, then there's our tangent line, right? Okay, so that's all we need, right? If we're trying to approximate the value of the function here, the approximate value of the function is right there, right?
Hold on.
Okay, you guys got to get this. I mean, a lot of you guys missed this the other day. If you don't pick this up here, you're out of luck.
So
You gotta really focus on it.
it.
Yeah. Right. So we're trying to approximate what is f of x plus delta x. That's the value of the function. There's f of x plus delta x. But we don't want to go through the exact calculation. We're going to estimate it with our linear model. So here's the estimate right there. That's what we're trying to find. What is that? Well, this height right here, look, what are the coordinates of that point? You know, that's just f of x, right?
X.
So this y value is just f of x, right? This distance right here, this is our differential approximation for how much the function is changing. That's dy. Yep.
So why don't we just use the things
It is. That's what we're doing. That's what we're doing. So our estimation of the value of the function here is the value at x plus dy, which is the calculus part. That's our differential, right?
So is this like where we go like the square root of 100 and dx is equal
Yeah,
to
right.
minus 1?
Right, so we would look at this then, let's take this square root of 99. The square root of 99 we could think of as the square root of 100 minus 1, right? Right, so that looks like the f of x plus delta x, right? So now let's just focus on that part. I'm going to get a new page, and that's all we're going to look at here. It's just, I want you to see, if you can see that part, it's easy. It's really easy. So I need so we're trying to find the square root of 99, right? And we're just going to use our approximation. F of x plus dx, let's call it, is approximately equal to f of x plus dy. Right? So the square root of 99 looks like the square root of 100, which we know, right? Minus 1. So how is that So what's f of x then for us? Well, I mean, what's the function we're trying to? Square root. Yeah, right. So f of x is the square root of x. Okay. Now, what is x? X is the convenient value that we know. So what's x? 100. Yeah. X is 100. Now, dx is how much we're moving off. So that's going to be -1, exactly. So
what's dy?
dy is the approximately how much is our function changing when we scoot horizontally dx. Right? If we go back to, here's our picture, right? dy is how much when we go from x to x plus dx, how much did our function shift?
Oh, okay.
Okay. So then dx is -1, right? And so we can calculate dy pretty easily. dy, we know that's our definition of the differential. dy is just f prime of x dx, right? So if f of x is the square root of x, what's f prime of x? Well, this is same thing as x to the 1/2. So if we differentiate that, what do we get? Okay, x to the -1/2 times 1/2, right? And then we're going to multiply the whole thing by dx. So that's going to give us, we've got 1/2 x to the -1/2 just puts the square root of x on the bottom, right? Right? Everybody agree that's the derivative? Times dx just puts the dx on the top. Okay? Now, if we evaluate this with our chosen values of x and dx, dy is going to be really easy, right? This just ends up being, because we purposely chose x to be something that's a perfect square, right? So, oops, hang on. This is, here, let me backtrack just a tiny bit. That's f prime of x, so dy equals that times dx. Right? If I plug in the numbers, that's dx we said was -1. What? -1. Over 2 times the square root of 100. Well, what's that? -1/20, right? So -0.05.
Can you do that with, like, just, is it just in case just the change? Like, we find, like, the easy square root, we do change over the 2 times whatever, yes, the easy square root is.
Right. The whole point is that, notice when we do our differential approximation, yeah, we're doing a little calculus, but when we evaluate the derivative, we're evaluating it at our convenient value, and so it's just elementary arithmetic there, right? We can get a nice even number, okay? So then what's our answer? Well, our answer is f of x, so that's the square root of 100, right? F of x is the square root of x is 100 plus -1 over 2 times 10. So we get 10 minus 1/20. 10 minus 0.05, so 9.95. Right?
A little bit less than 10.
And what is it really if you plug in square root of 99?
I got one. You got it. Oh, you got it.
It's really equal to 9.94987, so we're pretty close.
So are you going to go like 3 decimals or something like that?
Yeah. And I'm going to want, obviously, the wrong answer. I want the right wrong answer.
Right.
I want the approximation. If you just put in square root of 99, that's not what I'm looking for. I'm looking for what the approximation is.
Wait, what's it really? It's 9.9.
94.
9.9487, and I'll probably have you go out to like 4 or 5 decimals so I can
Wouldn't it be the same
distinguish.
if you just rounded it though?
But I don't want you. I want to know.
What I mean, if you took the real thing and then rounded
Oh,
it,
it would
it'd
be.
the same
You're
thing.
right. You're right.
That's the wrong answer.
But to ensure that you're doing the right process to test your ability to do this, I'm going to have you put the wrong answer in out to like 4 or 5 decimals, so that you get the right wrong answer.
In this case, it would be the right answer rounded would be the wrong answer.
Yes.
That's
That
why
would be
they're
the wrong
on
answer.
so many decimal places.
Which would mean that all you would have to do is
Which would be the right answer.
The right answer to 4 places was 9.9487 something. But the answer I would want you to enter is 9.9500.
Or the wrong answer. minus
Yeah.
4 decimal places.
You see what I'm saying?
Wrong right answer.
Okay.
I was gonna put in a.
But you can't always bank on it being the same
Okay,
to a certain
yeah.
number of.
Okay.
Right. It's going to change every
Well, I
time.
mean, you could.
Well, that ain't
That'd be stupid.
But it wouldn't work. I mean,
Yeah.
if I had put in 98, for example, square root of 98, it wouldn't have been that close,
Okay.
right? And if it were a cube root of something that were right close, see, I mean, it just depends on the function. Okay.
How come this one was so close? The other ones that we did weren't.
Well, because the reason it's so close is because 99 is 99% of 100, right? If I did the square root of 9, or excuse me, the square root of like 15, then that's off by 1/16. That's a pretty significant margin. This is only off by 1/100. So the bigger the number is, the closer. If you're only one off from a really big number, that represents a pretty small percentage.
So then we could, if it was the like that, we could actually get the right answer, then subtract or find the 1/16, like you said, of the. Just,
Well,
you could, is what I'm saying. Though.
you mean to try to legally get
Yeah.
the right answer? No.
But if I said it was off by a factor of like 1/16.
No, you don't know. No, that was, what I'm saying is the argument of the function is not very different, right? So the square root of 99 is pretty close to 100. They're almost the same. But 15 is not as close to 16.
Even though it's still 1.
They're one off, but in an absolute sense, but as a percentage of the whole, that's like saying 1 is only 1 off of 2, but that's 50% difference. See what I'm saying?
Yeah, but
So the square root of 2 is a lot different than the square root of 1. But the square root of 100 is not that different from the square root of 99.
I mean, couldn't you kind of account for that? Figure
Well,
out?
no. This is the easiest way to account for it. You have to do the math. Okay, here's another one. Moving on. Okay, in the following equation, find dy and evaluate dy for the given value of x and dx. That's really no big deal. What do we do there? I mean, we just find the differential form of the derivative and plug stuff in, right? The differential form of the derivative here, this ends up being a really simple problem. Dy is just the derivative times dx, right? Well, what's the derivative of that function?
Minus 2.
Okay. Times,
And
Right.
plug in x and times it by dx.
yeah, that's it. Plug in x and dx and you're done,
That's what I do.
right? No big deal. But that's the power of this. It's pretty easy to do. It's pretty easy to calculate dy, but dy is a good approximation of how, potentially, of how much the function has changed. I guess it may let me draw an arrow.
Yeah, what's below the
Yeah, what's behind the
calculator work?
the right there? Can't see what's behind that.
Oh, it just says dx.
Yeah. Figure.
Okay. Okay.
Okay.
All right. Next. Okay. Find the differential. So what this is saying here, when it asks for a differential, this is just the derivative with the dx attached to it, right? That's all you're doing. The differential is just the derivative of this with respect to x, but then I'm going to multiply both sides by dx, right? So every time you're given, what you want to recognize here, every time you're given a standard form of a derivative, like for example, we know that the derivative with respect to x of tangent u is just secant squared u times u prime, right? If I want to write the differential form, now I want you to notice something here that's really important because this is going to have strong implications when we get to the next chapter. If I multiply both sides through by dx to get the differential form of this derivative, look what I get. Secant squared u. What's du dx times dx?
dy, du.
Yeah. So what you notice then is you can think of the differential form of the derivative as the way that we would slice this up into incremental pieces. Right? Infinitesimally small changes, vertical changes in tangent u are always going to look like this. Okay? So if I wanted to take pieces of something and add them up to get a whole, those are the pieces I'm adding up. Okay? There's no x's in there, right? It's just in terms of u's and pieces of u, small pieces of u. The main thing I want you to notice there is, look, no x's. The differential, you don't see any x's in this anywhere, do you? We're differentiating in differential form, right? We're just taking differentials of tangent u. So why would there be x's in that? There aren't, right? It's all in terms of u's.
So you just take the derivative and then tack the dx.
So
That's
let's find
it.
let's
That's
find the
exactly it.
differential.
That's all it is.
Let's
Just
find the
multiply it by
differential.
dx. Right.
Can we find the differential?
Okay. So then with this one here, this is just doing the same kind of calculus you've done in the past. If I rewrite this as a power, what does that look like? The derivative of what? To the 1/2. Hey, but you guys stop talking back there. It's just there's this constant
Worry
little.
about that math.
Okay.
Calculus.
Okay. So what if I differentiate that then using my chain rule? What do I get?
Feel like an onion.
Like an onion. So I get
1/2.
1/2 something
8 minus
to the
negative 1.
times the derivative of what's inside, which
X
is
minus 6x. Or no, 8, no. Negative 6x.
and then what goes on the end of its differential? dx.
You like that?
That's my answer.
Money.
Now I can clean that up. If I multiply 1/2 times negative 6, I get negative 3x dx on the top, and then that stuff just all goes to the bottom, right? Because it's a negative exponent.
Okay, whoa. where
Right.
is that?
But that's just cleaning it up, right? Because 1/2 times negative 6 gives me negative 3. There's my x. There's my dx. And then all this stuff right here
Okay, square. Okay, I got
goes to the bottom because it's a negative
Fast
exponent.
forward for seconds. Caught up.
Mr. Olaf?
Yeah.
You write in the blue the tangents.
Mhm.
Does that have anything to do with it at all?
None.
Okay,
No.
that's what we were talking about
Oh.
earlier. We're confused.
No, nothing. The point of that stuff was just that when you take when we take a differential form of a derivative of anything, if I'm given this standard form, this is just one of our derivatives we know, right? If I want to write, there's a differential form of that derivative that's equivalent. If I don't write the derivative with respect to x, if I just take a differential derivative, then look at the answers. They're the same. The only difference is the dx has gone away in the bottom. Instead of a u prime, it's just a plain old du. Okay? That may seem a little weird. And it's okay if it seems a little weird, even after today. When we do integrals, though, that's going to be a big deal. We're going to come back and we're going to use, when we solve, for example, we're going to do something really important called solving differential equations. And to do that, we've got to differentiate both sides of an equation without respect to anything. We're just going to differentiate them in differential form. When we get there, it'll make sense. Now it just sounds like a bunch of gibberish, probably, but
So,
jibber jabber, jibber jabber.
why would we do that? We haven't got there yet.
We haven't gotten there yet. Right, but it's important in this section because that's how we do differentials, right? When I want to do a differential, it's just dy. And that's our linear approximation of the change in a function. Yeah.
Okay, this is a little off topic, goes back to the finding the approximation root. Where am I going to use that like other than a math word?
You won't, but it's just a convenient way to test this, to use this. instead of a square root function, it probably would be something like an actual function that you're approximating. But you can do this. I mean, that's a pretty slick way if you want to, if you didn't have a calculator and you wanted to get a good approximation of a square root, you could do that in your head. If you knew a little calculus, it's not that hard. I mean, if you've done a few of them, the derivative is easy and you're analyzing it, the numbers are round. So it's a great trick at a party. It's a nerdy trick to really impress everybody around you that you can do the square root of 123 to probably within 4 decimal places. People will be flocking to you. You'll be the most popular person at the party because no one else will be able to do that stuff. And that's what everybody wants to be able to do in life, right?
That's a good pickup
Before
line.
the party.
There's a class called party tricks.
That's how I met my wife.
Oh, man.
I don't know if that's a good thing or not.
Okay, so
I don't think that's.
each function, now let's look at this one here. Each function f of x changes value when x changes from x sub 0 to x sub 0 plus dx. Same stuff we're doing, right? All they want to do here, no big deal. In fact, I don't really like this problem that much, but it's a pretty common calculus problem, so I'll probably make you do it. They want you to do 2 things. They want you to find the actual change in the function, which we could call delta f, which is literally just the value of the function at -2 plus 0.1, right? So if x sub 0 is -2, then x sub 0 plus dx is just -1.99. So that's literally just saying we would find the value of the function at x sub 0 and the value of the function, so at -2, and the value of the function at -1.99 and subtract the two, the absolute value. Subtract them and just take the positive difference, right? That is what we call delta f. That's it. Okay. So to find delta f, and you would actually have to take the absolute value. It could have a sign on it. That's okay. So that's going to be the actual change in the function. Now the approximate change in the function is that differential stuff we've been talking about. So that's just going to be the derivative of the function times dx. Right? To find out the error in using our approximation, all we have to do is just, what's the difference between the actual answer and what we predicted? So it tells you how to do it. You're just going to take the absolute value of delta f, the real change in the function, minus the approximate change in the function. That's all they want.
Can we do it? 'Cause it
Yeah,
it makes
let's-
sense when it's explained, but it always makes sense when we do it.
Okay, let's do it then. So we end up with delta f just equals f of x sub 0 minus f of x sub 0 plus delta x. Okay, so that's just f of -2 minus f of -2 minus 0.1 plus 0.1, sorry. And we would just put those in our calculator. So what do we get then if we plug in, what is this function evaluated at -2? So I'm going to get, what, 12 minus 4, so 8, right? What is this function evaluated at -1.9? Well, I can't do that in my head, but somebody put that in your calculator. What's 3 times 1.9 squared minus 3.8? Not much.
Wait, just say, what did you say? Back, I didn't.
3 times 1.9, negative 1 point, no, 3 times 1.9 squared minus 3.8.
3.8, oh, okay. 7.3. That's what I got here.
7.03? Is that far off?
The 1 point something squared, then.
It seems like that's too far off.
I know the answer in my head.
So that is 7.03. Okay. So we get 0.97. So delta F, the actual change in the function, it changes by an amount 0.97. Okay. Now what's the approximate change in the function? What's df? Well, df is just the derivative, which is what, 6x plus 2 times dx, right? So that's 6 times negative 2 plus 2 times 0.1. So let's see. So we get. Oh, yeah, I did that backwards, didn't I? I wanted to do this minus that. Whoops.
Yeah.
So that should. We want the opposite, right? Everybody see that? Delta F should have been my mistake. Delta F should have been right.
Kidding me?
I just flipped it around, so it should have been that number minus that number. Everybody see that? I'm sorry about that. Okay. So. 7.03. So if I did that, that would have ended up being 7.03 minus 8 equals negative 0.97. So that's our answer. Okay. Now what about df? df is, let's see, negative 12 plus 2 is negative 10 times 0.1. Well, that's just negative 1. Right? So the approximate change in the function is negative 1. The actual was negative 0.97. Right? Now what does it want us to do? I think it wants us to calculate, the approximate error. So it wants us to calculate the absolute value of delta F minus df. Okay, we can do that. So the absolute value of delta F, which is negative 0.97 minus negative 1, right, is the absolute value of 0.03, which is just 0.03. And do they want that as a percent? No. So as a percent, it would be 3%. That's the difference, but they didn't want that. They just wanted to know what's the actual error associated with it. So our approximation is actually off by 0.03.
It's useless.
Well, no, maybe that's okay. Maybe that's within acceptable error. Who knows?
The building thing, maybe it won't crash.
Right.
Like,
Good enough.
Okay, this is, I mean, you wouldn't always use these things, but sometimes you can. I mean, it makes it easier. Look how easy it was to calculate. That was easy to calculate, wasn't it?
Yeah.
A lot easier than that.
it could be 3% off.
Okay. Okay, last two. These are the important ones, most important ones. Use differentials to estimate the maximum error in measurement resulting from the tolerance of error in the dependent variable. All that's saying is, if we're going, how much error is propagated in the calculation? If there's a certain amount of error in making a measurement, then how much is that error propagated when we do a calculation with that measurement? That's all they're saying, right? So we want to find dB. That's it. What's the approximate, uncertainty in the volume calculation, which we call dV. Okay. So if V, what is the formula for volume of Q?
It's next to the third.
Okay. So then what's dV?
Right. What? And then
Yeah. So there's the approximate propagated error, and that's all they're asking for. It could be off by as much as what? So if we plug numbers in, 14 is x, dx is just this, right? Right, that's the measurement error. And so we get an answer of 4.2, plus or minus 4.2. And the units would just be square or cubic centimeters.
Is that all the way? Yeah.
Yeah, that's it. Could be off by as much as 4.2
Why isn't it?
cubic centimeters.
When do we use this DV11?
Well, okay, that's the next one.
Right there.
Now, in this case, notice that here's a question. Yeah?
Why is it 3 times 14 instead of 3 times 14 squared?
Oh, you're right.
So
Because I didn't forget to put squared up there. So that's going to be off by a little bit. Let's redo that. All right. So 14, whoops, forgot my squared again. So 14 squared is what, 196?
Yeah.
Times 3 is what? 588. Yeah, 588 times 0.01 is 58.8. Okay.
Way off.
Yeah. Well, okay, but here's now Chad's question was a good one because is that way off or not? We don't know. It depends. What if the volume is 1,000,000 cubic centimeters? Then that's pretty good. If the volume is only 200 cubic centimeters, that's pretty bad, right? But all they wanted here, they wanted to know, they wanted a number. They didn't want a percentage. They wanted to know the estimate of the volume could be off by how many cubic centimeters? By that much. Okay? The key is that they were asking for something that had units, right? So they actually wanted to know what is dV. Okay, now a better question. Really, this is, I mean, that's sometimes valuable to know, but a more important question to be able to answer would be one like this, where they want a relative error. Because then we're getting it in terms of a percentage, and so we really know, is it good or bad? Okay, yeah, we'll finish. So the edge of a cube is 15. Now this time, we can measure the edge of a cube with an error of 1%.
So it's just
The cube's volume is going to be measured, and we want to estimate the percentage error in measuring the volume. Okay, so there's a couple ways we could go about this. Now we could turn that into a number, right? So we know that x equals 15 centimeters plus or minus how much if it's 1%? Yeah, 0.01 of that, right? 1% of 15 would be 0.15. Right? I mean, hang on. It'd be, you gotta move it over, you gotta multiply 15 times 0.01. So we're gonna move it over 0.15, yeah, plus or minus 0.15 centimeters. That's 1%, right? That's our 1%. Okay? Right? So then what's x? Well, I used x for side length.
This is cube, right? Yeah.
So this is x, and that's dx, right? X is the amount, dx is the error, measurement error. Okay? So then if v, just like before, if v is x cubed, dv is just 3x squared dx, right? And what we're trying to find here is the percentage error. That's a relative error. So we want dv over v. We want the error in volume as a fraction of the whole volume. So what we're trying to calculate is this, dv over v. Well, what's dv? It's 3x squared dx. What's v? It's x cubed,
Yeah.
right? And so we don't want to just plug numbers in there. We'd rather do this instead. We would rather say, okay, well, x squared over x cubed just leaves me an x on the bottom, right? Now, here's the trick. Watch this. Did we even need to know what dx was? No. Now, just watch this. This is really cool. And then we're done. 3 times dx over x, I could say, is 3 times plus or minus 0.15 over 15. That's going to give me the same answer I would get if I thought about that as being 3 times dx over x. without ever calculating what dx is, what does that represent?
0.01.
Yeah, that's the relative error in measuring side length, isn't it? Which they told us is 1%. How about that? Right, so I know, I mean, I don't have to do it that way, but isn't that slick? I could plug in a number there for this whole thing. That's plus or minus 0.01. Right? Because of this statement right here. Right? That is dx over x, isn't it? Because it's the relative error in measuring x. So dx over x. Well, you got to multiply it by 3. So it'd be plus or minus 3%. But you see, I mean, we could also do it this way. It's fine. If we had plugged this in, look what we would have gotten. We would have gotten, if we had done that calculation, we would have gotten plus or minus 3 times 0.15 is 0.45 over 15. Well, what's that going to be? 3%. 3%. Yeah. Either way.